In this paper, we aim to achieve faster neural networks. We first call for tracing higher flops per second beyond simply reducing flops. That is, to push the utilization of computational capacity as high as possible. Following the principle, we propose pconf, a simple yet fast and effective operator. It takes advantages of visual redundancy and applies a regular convolution on only part of the input channels, while leaving the remaining ones untouched. By nature, pconf have lower flops than the regular conf while having higher flops per second than the depthwise convolution and the group convolution. Building upon our pconf, we further propose FastNet, which runs fairly fast on a wide range of devices and tasks without compromising the accuracy. Now, let's dive into more details. Neural networks are everywhere, from image or video classification, detection to segmentation. And we need fast neural networks for instance response, for safety reasons, to improve user experiences, and to protect user privacy. How to be fast? There has been lots of work on this, for example, from popular mobile nets and shuffle nets to more recently proposed mobile VIT and mobile former. Then many focus on reducing the total computation or FLOPS. However, are they really fast or fast enough? Not really. The latency of a neural network can be calculated as the ratio of FLOPS over flops per second. Existing neural networks are effective in reducing flops, but they sacrifice in having lower flops per second. As such, their latency improvement can be unclear or ineffective. To better understand the situation, we compare the flops per second of typical neural networks on a CPU. The results show that many existing neural networks suffer from low flops per second, generally lower than the popular ResNet 50. With such low flops per second, these networks are actually not fast enough. Their reduction in flops cannot be translated directly into the exact amount of reduction in latency. In some cases, there is no improvement, and it even leads to worse latency. For example, Cycle MLP B1 has half of flops of ResNet 50, but runs more slowly. But why? What slows down their flops per second? To answer this, let's compare the convolution and the depthwise one that was commonly used in those networks. Note that the width or the number of channels is normally enlarged for the depthwise conf to compensate the accuracy drop. This, however, incurs excessive I/O memory access and slows down the computation. To quantify this phenomenon, let's examine how many memory access are spent for each flop. Here are the ratios for conf and depthwise conf, respectively. After several steps of cancellation and approximation, the depthwise conf has 128 times more memory accesses than the regular conf, as a typical example. This has also been noticed in previous works, but remains unresolved. The depthwise conf is still widely adopted, and it seems that there are no better alternatives. But really, can we save the I/O memory access and improve the situation? The answer is yes, with a pretty simple idea. The feature maps are redundant and sometimes highly redundant. Therefore, we can apply filters on only part of the input feature maps. We call it partial convolution. Its advantages include having fewer flops, consuming less I/O memory access, and maintaining high flops per second. For continuous memory access, we consider the first or the last consecutive part of the channels to compute, as illustrated in the figure. Now, we compare the ratio of memory accesses divided by flops again. pconf has only 4 times more memory access per flop than the regular conf, much better than the depthwise conf. We also compare the on-device flops per second on GPU, CPU, and ARM processors. We are unsurprised to see that the regular conf has the highest flops per second since it has been constantly optimized for years, and for pconf, it achieves impressively from about 6 to more than 20 times higher flops per second than the depth-wise conf. pconf is fast and also effective. We replace the convolution in ResNet 50 with relative variance and adjust the network width to facilitate comparison. Results show that pconf improves ResNet 50 in accuracy by a clear margin while being faster than other variants. To fully leverage the information from all channels, we further append a pointwise convolution to allow pconf. Their effective receptive field together on the input feature maps look like a T-shaped conf, which focuses more on the center position compared to a regular conf. This T-shaped receptive field is reasonable as we empirically justify. We evaluate the importance of each position by calculating the position-wise Frobenius norm. We assume that a position tends to be more important or salient if it has a larger norm than other positions. Results show that the center position turns out to be the salient position most frequently among the filters of a pre-trained ResNet. We also show that a pconf followed by a pointwise conf is effective in approximating a regular conf compared to other combinations. Starting from our pconf, we further propose FastNet. We keep the architecture as simple as possible to make it hardware friendly. It has 4 hierarchical stages, each with a stack of FastNet blocks. Within each block, a pconf is followed by 2 pointwise conf. We put normalization and activation layers only after the middle layer to preserve the feature diversity and achieve lower latency. FastNet stands out by being faster and more accurate. For example, it's 2 to 4 times much faster and nearly 3% more accurate on ImageNet than the mobile VIT. FastNet is generic for various computer vision tasks and is applicable to diverse devices. Here is the comparison of trade-off between ImageNet accuracy and throughput on a GPU. FastNet achieves the state-of-the-art trade-off. We also compare the accuracy and latency trade-off on a CPU and on a more low-end ARM processors of a Raspberry Pi. The advantage of FastNet is consistent. We further conduct experiments on the Coco dataset for object detection and instance segmentation. FastNets are competitive in both AP scores and latency. Thanks for your attention. For more details, please refer to our paper and code.